All right, so you guys heard our friend's answer. You need a new law, when you observe a phenomenon that is not explained by existing laws. Okay, so let me give you an example of that. But before we do that, you guys know what is conservation of energy? What is the conservation of energy principle?
Can't be made or destroyed.
Can't be created or destroyed.
Yep. So what does that mean? Everything in that happens in nature, all that's happening is energy is being moved from one place to another. Okay. It can be converted from one form to another. It can move from place A to B, but you can't create it or destroy it. Okay. So now let's look at something. Yeah. Here's a glass of water. It's at 50 degrees Celsius. It's in a room where the temperature is 20 degrees Celsius. What will happen?
The water will cool.
The water will cool. Heat will move from here to there. What is heat? Heat is energy. Okay? And heat moves from there to there. And the temperature, I'll just make up some numbers. That's what happens. Okay? Why doesn't the opposite never happen? Degrees Celsius. See, all that happened here was energy moved from here to there. All I'm asking is, energy moved from here to there. It's still in agreement with that law, conservation of energy principle. Energy wasn't created or destroyed.
It's not impossible for that to happen, but it's highly unlikely because that is a more ordered system than if they were both 21 degrees Celsius, because more energy is contained within the cup of water.
Okay, so.
It's lazy.
I'm sorry?
It's lazy. The energy.
Oh, the energy is lazy.
Doesn't want to put in work. Mm-hmm. Yeah.
Science
Hmm?
we did science sheet, right? Or you already did it?
The more important thing is you're late and you're missing the lecture.
You almost hit me in the parking lot.
No, she jumped out. She jumped out in front of me. You don't listen to her.
It doesn't matter. You're hurting yourself. And you don't even pay attention in class, so that's a different matter. All right. So our friend here made an important statement. It's not that this doesn't happen, it's very unlikely to happen. How unlikely is it? Do you know how old the universe is? 14 billion years old. You can wait trillions of universes, and maybe one time it might happen in a trillion times. So it practically is impossible. It doesn't happen. Okay. So here's something that you observe every day. Energy doesn't move from here to there, which the conservation of energy principle is cool with. Okay. So this doesn't happen, and so we need a new law. And the new law is simple. Only the phenomena that you observe, what happens is only phenomena where the entropy increases will happen. Entropy of the universe increases, only those will happen. So in this case, entropy is denoted by S, this will happen. In this case, entropy would decrease and this doesn't happen. So that's your new law. And that's this chapter. Okay? Everybody understand? It's that simple. All right, so now we'll get into the slides. Yeah. So we're talking about the second law of entropy, second law of thermodynamics. It expresses the existence of a quantity called entropy of the system and states that the entropy of an isolated macroscopic system never decreases. So if you have an isolated system, no matter what you do in the system, the entropy will never decrease. All it can happen is stays constant or increase. Yep. What is the ultimate isolated system? The universe. So the entropy of the universe can either remain constant or increase. Yep. Yep.
Is there another example of an isolated macroscopic system, or is it just universe?
Yeah, I mean, in practice, you can't. You can't do anything. I mean, even you take a galaxy, you exchanging electromagnetic energy with. So you can't exchange any energy with anything else, with your surrounding. That would be an isolated system. Yeah. Okay, we already talked about reversible and irreversible processes. A process is irreversible. Okay. So you saw that you have a hot cup of water, you place it in the room. What happens is heat moves from there, and this is where the universe goes. This process would be reversible if you could take the surrounding and the system back to its original state. Okay? So this process would be reversible if you could take the surrounding and the system back to its original state. And there's no natural process that occurs where you can do that. Okay? So you can remove heat from here and put it there. Okay? So you could make this warm in principle, but what you'll find is the surrounding will be warmer in practice. Okay? So you cannot, in all the processes that we see, the system and the surrounding can never be taken back to the original state. Okay? So all naturally occurring processes are irreversible. Yep.
Then why do we talk about it at all?
About what?
Everything we see is irreversible.
Right.
Why distinguish the difference?
So the reversible process, I mean, in mathematics, you have talked about asymptotes. This function is not ever going to reach that line, but that line gives you the upper limit for the value of the function. You know, so. I'm sorry?
So that's a bit valid point.
Yep. Yep. Well, I mean, yeah. People are smart. I mean, people have been smart for a long time. So when we do something in science, we always do it for a good reason. I might not be able to explain it, but you know, so there's always a good reason. All right. Okay, so a reversible process is one where you can take the system and the surrounding back to its original state. Okay? All natural processes are irreversible. All naturally occurring processes are known to be irreversible. Okay, so you guys saw this. So this is the example we started off with, the lecture with. The first law of thermodynamics, which is a conservation of energy statement, has no problems with the heat flowing from it. The first law of thermodynamics has no problem with heat flowing from here to there and the system evolving there. In this process, you didn't destroy energy, but you never observe this in nature. Okay? And so the new law that we have come up with says that if this process happens, then entropy would decrease for the universe. And a process where the entropy of the universe decreases doesn't happen. That's the new law, that's all. Okay. Okay. You look like you wanted to say something.
No,
All right.
thinking real hard.
You were done?
Thinking.
Yeah. It's. I'm glad to get under your skin. No, it's. It does require some thought. Okay. So here's another example. Okay. So here's a cup at 40 degrees Celsius, ice, and heat flows from there to there, and the water will melt. And the opposite, you never observe the opposite happening in nature. So all real life thermodynamic processes are irreversible. All real life processes, thermodynamic processes that are occurring in systems that have a large number of particles. Okay. And like our friend said, the opposite can happen, except that it'll happen in a trillion lifetimes. Okay? Not lifetime, universe lifetime. So this quantity, we're defining this new quantity called entropy. It's denoted by S. It's a measure of disorder in the system. It's a state function. What does that mean?
It doesn't matter how you get there.
Yeah. So we've been doing PV diagrams. So the state of a system is given by values of various thermodynamic variables. So in this graph, we are only showing two thermodynamic variables. So it's a state function. It just depends on the state of the system. It doesn't matter how you get there. What else is a state function?
Speed.
Energy of the system, and you can see that pressure, volume, temperature, all these are state functions. Okay? It doesn't matter how you got there. Okay? All right, so thermodynamics is a new variable that's a state function. So the reason we talk about this is when you go from here to there, the change of the value of that function doesn't matter how you go from here to there. If you have $100 here and $200 here, the change, or $300 here, the change is $200. It doesn't matter how you go from there to there. Yep.
So you say it's measuring the disorder in a system. You mean it's like basically measuring the kinetic energy? Like how much the molecules are moving around randomly?
No, disorder is, okay. So, okay, I'm just going to give you a simple sort of made up example.
Okay.
Okay? Well, it's not made up, but it's, it illustrates the point. All right, so let's say you have all these slots and you have 5 marbles.
Okay.
Now let's count the number of ways these 5 marbles can be arranged.
Okay.
There's 1. Here's 2, and so on. Okay. The more ways you can arrange a system, so for a given total energy, the more ways you can distribute that energy in the system, the more disorder there is. Okay. So for instance,
So it's almost like randomness or like possibilities.
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 Mm-hmm. Okay, so entropy is a state function, um, just as temperature and internal energy, okay, pressure, volume, and other. Change in entropy during a process depends only on the initial and final state. So change in entropy only depends on the initial and final state, okay, just like for all these variables. It doesn't matter how you get there, okay. So for instance, your bank balance is a state function. You can go from this bank balance to that bank balance. There's a zillion ways to go there. Spend more, earn more, this, that, you know. So, I guess so. Calculating entropy by itself is very hard to do. Okay, so if you ask me to calculate the entropy of this gas in this room, that's very hard to do. Okay, so in practice, what we do is, in practice as engineers, what we do is we can calculate the change in entropy in going from initial to final state. Okay. And that too, you can't do this. This is hard to do quantum mechanically, or yeah. So we can show how to do this in practice. Okay, so entropy of a system can be calculated one or two equivalent ways. Change in entropy in terms of the heat gained or lost and the temperature of the system. Okay, so what do we mean by that? So here is the infinitesimal change in entropy. The amount of heat absorbed by the system divided by the temperature at which this heat is absorbed. What's this temperature? What units are the temperature in? Kelvin. So in thermodynamics, you always take Kelvin. Okay? So this is the infinitesimal change in entropy. Okay, and so if you're taking a finite journey, you guys are all integration experts. So you just do an integral. That's it. Okay? Take the change in entropy for a small step, and then just add them up. So this is how, in practice, we calculate the change in entropy. You know? The second way we calculate is in terms of the number of possible microstates given a macrostate of the system. Microstates is, remember when I was trying to arrange those atoms in the slots? Each arrangement was a microstate. Okay. So for given those 5 marbles in 20 slots, that's the macrostate. For that macrostate, how many microstates can you have? Or you can think of the gas in this room has 100,000 joules of total energy. How do you distribute that 100,000 joules of energy among all the particles? Okay, that would be the number of microstates. S, for that, if you could calculate that, then S is the Boltzmann's constant times log of W. This is the number of microstates. Now, this fella is very hard to calculate. You know, people like Stephen Hawking used to calculate for black holes. Okay. Yep.
So, I guess the like for the gas in this room,
Mm-hmm.
will the molecules like always arrange themselves? So it's like the highest possible number of microstates?
Yeah, so the macrostate arranges itself such that, okay, so let's say in this corner we burn a bunch of physics books. Okay. It gets hot here. What does the system evolve towards? It'll evolve such that the temperature becomes even everywhere. Okay. Why did the system evolve from here to there? because this, with higher temperature, had fewer microstates. With even temperature, there were more microstates. Okay. So the probability of an even temperature is higher, of occupation of a high, even temperature is higher because it has more microstates. There's still something still bothering you. You sure?
Okay.
All right. All right. This this formula was derived by Mr. Boltzmann. And that's why we call that the Boltzmann's constant. Mr. Boltzmann is considered a top-notch dude. Einstein caliber. And see, he did many things, and that's what he's most proud of. That's his tombstone. Yep.
So is there like a cap number to the amount of microstates a system could have? Like if you just kept adding energy, it would just keep going up?
Yeah. But it'll always be less than infinity. It's a finite number. Extremely large finite number. Okay. All right, so you can calculate the entropy. If you want to absolutely calculate the value of the entropy, you can calculate it using this formula. Except that, like I said, this guy for a given situation is very hard to calculate. Okay. So in practice, this is the formula we use. You add a little heat to the system, divided by the temperature. That's the change in entropy, and then you just sum it all up. Okay? So in going from this initial state to final state, that's the change in entropy. Okay? That's what we calculate in practical situations. Okay? So that's that. Okay? So what is the second law of thermodynamics? In all natural processes, in all processes that occur in nature, the entropy of the universe is increasing. That's all. You had to get permission from her. All right. So here's a very good, important, here's a nice statement. The simple energy is the ability to do work. Okay? So if you have 100 joules of energy, you can do 100 joules of work. Okay. Entropy is a measure. So for instance, in principle, if you have a potential energy, if I have an object there, I can, so if an object is there, so if I have an object, this has potential energy, I can drop this guy and lift this up. So if I have potential energy, I can convert 100% to work. Okay? You have kinetic energy, you can do 100% to work. So back a couple of 100 years ago, once we realized heat was a form of energy, when we did the steam engine and stuff like that, the question was, how much of this could you convert to work? Okay? And we realized you couldn't convert all of the heat energy to work. Okay? Your car does 20% of that. Okay? It converts 20% to work. What happens to the other 80%?
Goes off in the atmosphere.
It remains as heat and goes out through your tailpipe. Okay? So energy is the ability to do work. Entropy is a measure of how much energy is not available to do work. Okay? So entropy is a measure of that. Okay. the unavailable energy is of interest in thermodynamics because the field of thermodynamics arose from the efforts to convert heat energy to work. Okay. Okay, so entropy is a state function. Change in entropy when you go from here to there doesn't matter how you get there. How many ways can you get there from here to there? Infinite number of ways. Okay. So if what we're saying is, if you evaluate this integral along any path, that value will be the same.
Really?
Yeah.
The area under the curve for any path?
No, this is a line integral, so
Oh.
yeah. It's not the area. Okay? This time it's not the area. So the value of that integral will be the same no matter what path you take. So what path are you going to take?
The shortest one?
The easiest one. Yeah. That's euphemistically the shortest path. Okay? So you're going to do the integral along a path. That is where the integral is easiest to do, and that's what we'll do. That's what we do in most situations. All right, so we'll sort of do an integral because it's easy. That's why, that's what we do in classes. We don't do any of the difficult stuff. All right, so here's an example where you can do that integral. And this is a sort of a canonical example. It's free expansion. Again, this is one of those idealistic things. Can't happen in real life. Okay, so what you have is two chambers. One is perfectly vacuum. Okay, is a perfect vacuum. When a gas is pushing against something, it's doing work. And when it does work, if you're not adding heat to it, where's the energy coming from? So internal energy, and you would cool down. The gas would cool down. All right, so here's perfect vacuum. You open the valve, the gas is expanding, but it's not pushing against anything. Right? It's not doing any work. It's not losing internal energy. Its temperature will remain constant. Okay? Now, again, you can start arguing against that. Once there's a little gas there, there'll be little pressure, and now it'll have to push. But hey, you guys didn't pay enough money to argue then, so we won. All right, so this is a free expansion. Okay? So the gas, if the temperature remains constant, you can connect those 2 points via an isotherm. Okay? So now we'll calculate the change in entropy along that path. When this free expansion happens, it turns out that the pressure and volume fluctuate. Okay? So really the gas is not expanding along that path, it's going along one of those paths, but we don't care. Those 2 points can be connected by an isotherm, so we'll go do the integral along the isotherm. So here is the change in entropy. We're going to do that integral along that path. All right, so here's the first law of thermodynamics. Change in internal energy is dq by minus dw. This is 0 since internal energy didn't change. You didn't do any work. Okay, so dq is equal to dw. dq is dw, which is p dv. And you're doing the integral along an isotherm. pv equal to nRT. In an isotherm, temperature is constant. Okay, so P is equal to nRT over V. P is nRT over V, and so this becomes the T cancels dV over V, and you do the integral, it's nR log of V final over V initial. So the change in entropy between 2 points, if you can connect them via an isotherm, then the change in entropy is given by that. Okay. N times R times log of V final over V initial. Okay. All we've done is we've shown you how to calculate the entropy for a simple case. Okay. But this is to really show you that in principle it can be done. Okay. Now here's a general case where the 2 points are not connected by an isotherm, okay, where the 2 points are such that the temperature and volume changes. Okay. And so the change in entropy can be shown to be that. N CV times log of T final over T initial plus NR log of V final over V initial. What kind of system does it have to be for that formula to be valid?
Constant volume.
It has to be an ideal gas system. We use those formulas, okay? So we are showing it for very specific. Okay. By the way, for the free expansion case where the temperature was constant, see this would be 1, this would be 0, and you get back your other expression. Okay. So this expression is a special case of this expression. Okay. Okay, so here is the statement, finally the statement of the second law of thermodynamics. Okay. The entropy of a system and its surroundings, which is the universe, increases during irreversible processes and can remain constant during reversible processes. How many reversible processes are there in the universe? None. Okay. It never decreases. All right, so for all real processes, it's greater than 0. Okay, so that's entropy. Now we'll go to the practical side. We'll talk about heat engines. What are heat engines? What are heat engines?
They convert thermal energy to mechanical energy.
That's right. Heat engines. The input is heat, and the output is work, mechanical energy work. Okay. So here is sort of a cartoon of a heat engine. You take heat from a heat reservoir, convert some of it to work, and then dump whatever you can't convert into the environment, into a cold reservoir. Of course, we'd like to convert all of it to work, but it's not possible. Okay, so for instance, your car is a heat engine. The reservoir is the pistons where you're burning the gasoline air mixture. You're converting some of that to the motion of the car, and the rest you're throwing out the window. Or not out the window, out the tailpipe. Okay. In a coal power plant, you're getting heat by burning coal, converting that to electricity, and throwing out some of the unusable heat. So, these are real numbers. Let's say you absorb $1 trillion worth of heat. We do this yearly. $1 trillion worth of heat, we convert $300 billion of it to electricity. $700 billion worth of it is being thrown into the environment. Real money. Okay. Anyway, so that's a heat engine. So what would you like to do? what would you want for your heat engine to be?
More efficiency.
As efficient as possible. So we want to know the upper limit of efficiency of a heat engine, okay? And we're going to give you that. So heat engines are devices that convert thermal energy to mechanical energy. All heat engines have a working substance that goes through a cycle. In an automobile engine, the working substance is the gasoline-air mixture. Do you want to see a simulation of a automobile engine? What? Yes? Everybody wants money.
Let's start at a single piston, the powerhouse of the engine, and work our way outwards. The four-stroke cycle. When a piston travels to the end of its range, whether up or down, that's a stroke. Car engines use a four-stroke cycle, and it goes like this. First, intake. The piston descends, sucking an air-fuel mixture into the cylinder through the intake port, with both intake valves open. Next, compression.
Okay, so you've taken an air-fuel mixture, and when you burn it, that's when you'll release heat, and you're going to convert some of that heat to work. Okay.
With all valves closed, the piston comes back up, compressing the fuel and air mixture for more powerful combustion. Then, the power stroke.
All right, so you have the air-fuel mixture, you compress it to warm it up. Why do you do that? Hmm?
Ignite the,
When you ignite it, you want all of the fuel to burn. One of the things that happens is when you're compressing it, it's warming up. And if some of the fuel self-combusts, that's called pre-knocking, you're working against yourself. You're wasting energy. So how do you solve this problem? So,
lead,
huh?
add lead.
So when you are compressing it, it's warming up, and some of this fuel self-ignites, and you're wasting energy. So don't put fuel in it. Just compress air. That's what a diesel engine does. In a diesel engine, you're compressing just air, and then in the hot air, you're inserting diesel fuel. Okay? Yeah.
An electrical spark ignites the compressed fuel and air mixture, and the resulting combustion forces the piston
now
to
the
the
heat
bottom
is
of the
doing
cylinder
work.
again. A connecting rod transfers this power to the crankshaft. Finally, exhaust. The piston comes back up, pushing the spent mixture out through open exhaust valves and the exhaust port.
So you got to recharge now. Okay? All right. All right, so the efficiency of a heat engine is you absorb, the H is the heat absorbed from the hot reservoir. How much of that did you convert to work? So the efficiency is how much, so this is the efficiency of it. So you absorb heat from a hot reservoir, convert some of that to work, and then dump the rest in the. Okay, so when the question arose, what is the best you can do, Mr. Carnot answered that question. Okay, so he considered a theoretical engine where all the processes, Carnot, a French engineer, showed that a theoretical heat engine in which all processes are reversible. That's an ideal engine. Okay. And no energy is wasted due to friction, and turbulence is the most efficient engine possible. all engines are less efficient than Carnot engines. So Mr. Carnot gave you an upper limit is what he gave you. And a Carnot engine, which is an ideal engine, establishes an upper limit for efficiency. All right, how much work can any engine do? Well, you absorb this much heat and you dump this much. So that's all the work you can do. Yeah. So the efficiency is the work you do divided by that. And if you substitute that here, so the efficiency of any engine, heat engine, is 1 minus QC by QH. And what Mr. Carnot showed that QC by QH is equal to TC by TH for an ideal engine. Yeah. TC is the temperature of the cold reservoir. TH is the reservoir, is the temperature of the hot reservoir. Okay. And these temperatures are on Kelvin scale. Okay. So this is the maximum possible efficiency of an engine. And look at this expression, it's very neat. What's neat about it?
Always positive.
Huh?
It's always positive.
Well, efficiency is always going to be positive. This is also always positive. See, it doesn't tell you how the engine is made. The highest efficiency just depends on the temperature. We don't care how you make it.
So like you might go with a six-stroke engine?
Yeah. There's no details about the engine here. All it's telling you is the temperature. What would you want the efficiency to be? Ideally, 1, if you could convert all of the heat to work. How do you make this 1? You had to make this 0. How can this be 0? If this is 0, that is you're dumping exhaust to absolute 0. Not possible. This could be infinity. Also not possible. Yep. But anyway, so that's what Mr. Carnot showed, that QC by QH is TC by TH. Okay. So in a reversible engine, the two cycles are isotherms and adiabatic processes. And when you come back to the starting point, the total change in entropy is 0 because you come back to your initial point. And during the isotherm, you're absorbing heat. So the change in entropy is QH by that. This is an adiabatic process. You're not absorbing heat. And here, you're dumping heat, QC by TC. Anyway, this is what Mr. Carnot showed. So this is an upper limit for the efficiency of a heat engine. The maximum possible efficiency for a heat engine. If your car engine were a Carnot engine, its efficiency would be 70%. In actual practice, your car is 25% efficient. Mm. So there's a lot of room for improvement. Okay, now we'll see refrigerators. What are refrigerators? What are these guys?
Keep your food cold.
What refrigerators are the following. Inside your refrigerator, it's 5 degrees Celsius. In your kitchen, it's 22 degrees Celsius. A refrigerator will move heat from here to there. Okay. Against nature's wishes. Well, so to do that, you have to do work. It has to be plugged in. The instant you unplug it, this thing will stop. Okay. So the question is, how do you move heat from a colder region to a warmer region? All right, so to understand that, let's go back a couple of chapters. Let's say I have a gram of water. I want to convert it to steam. What do I need to do when I convert water to steam? I'm sorry? Boil it. You have to add 540 calories of heat per gram. Okay, so that's the latent heat of vaporization. So when this liquid vaporizes, it absorbs heat. And then when you condense it, when the vapor goes back to liquid, it will give off that heat. Okay, so when a liquid vaporizes, it absorbs heat. And then when it condenses it, when you condense the liquid, it gives off that heat. So I gave you the secret already. Okay, so you want to remove heat from here, you vaporize a liquid inside here. You want to dump the heat here, take those vapors and condense it out there. That's a refrigerator. Did you guys understand that? All right. So you take a coolant here. All this has to happen in a closed pipe. You vaporize the coolant in here. You vaporize that liquid here. It absorbs heat from inside. You bring that liquid out and condense it here. It dumps the heat out in the kitchen. Yeah.
So you have to have a liquid that vaporizes at 5 degrees Celsius.
So if you want to have 5 degrees Celsius here, you have to have a liquid that vaporizes at less than 5 degrees Celsius. But very good observation. So if you want to make a freezer that cools down to minus 30 degrees Celsius, what do you have to do?
Vaporizes at -30 degrees.
Less than negative 30 degrees Celsius. Yeah. All right, so you guys understand how the refrigerator works? So you have a closed system. When some liquid evaporates in here, it absorbs heat, bring it outside, condense it, and then it'll dump the heat out. Okay. The coolant is vaporized in the evaporator. The vaporizing coolant extracts heat from the refrigerator. It is then compressed and sent through the condenser where it exhausts the heat to the outside. So you've accomplished this. Okay, so to run the compressor, you need work. You need energy. Air conditioners and refrigerators are heat pumps. So what is an air conditioner doing? It's removing heat from this cold room and dumping it outside. Heat pumps, in the winter, they'll extract heat from the cold air outside and dump it into your warm room inside. Okay? So they're all working on the same principle. Okay? They call it a heat pump. What does a water pump do? Moves what? Well, water will flow from a tank down on its own.
Moves it uphill.
And there you go. Yeah, I knew what you meant. I just had to. So, water pump moves water against gravity. A heat pump moves heat against its natural tendency to flow. So that's why the name. Okay, so for a refrigerator, we define something called a coefficient of performance. Okay, here's what we want to do. So for a refrigerator and a heat pump and all that, what we want to do is remove heat from a cold region and then dump that heat into a hotter region. Okay. The question is, to remove this much heat, how much work did you have to do? Okay. So the coefficient of performance is you remove this much heat and you had to do this much work. Okay, so here again the upper limit for an ideal refrigerator. It's related to the temperature, just like Mr. Carnot. Again, all these temperatures are in the Kelvin scale. Typical coefficient of performance of household refrigerators is about 5. What that means is for every 5 joules of heat you remove, you're doing 1 joule of work. Okay. All right, guys, so that